As we saw in our last conversation, the 20th century sat at an interesting intellectual crossroads. The Enlightenment of the 17th and 18th century held up reason as the defining characteristic of humanity and saw the advance of knowledge as the hallmark of human progress. The Romantic movement of the 19th century was a backlash against what it saw as the arrogance and naivete of this reduction of the human to its brain. As such, there was a divide in the intellectual world between the sciences and the arts. The sciences largely bought into the Enlightenment presuppositions that the world was well behaved, regulated by absolute laws that were accessible to human reason through rigorous processes of observation and logic. Acquisition of an understanding of these laws was paramount in our striving to move forward as a species. The practitioners of the arts and letters, on the other hand, saw themselves as the loyal opposition, needing to correct what they saw as the overreach of the sciences, which seemed to miss the beauty, the joy, the experience of being human. The heart was as important as the brain, and the fetish that scientists held for knowledge limited their true understanding. But this divide was not impermeable. As we'll see, there are important influences in both directions. The advances achieved and the difficulties experienced by the sciences changed the way we saw the universe, the world, and human nature, and this affected what was painted, built, written, and composed. Art reflects the world, but the world is never given to us directly. As the late 18th century philosopher Immanuel Kant pointed out, our understanding of reality is always mediated through concepts we use to create the ideas in our mind that only seem to come fully formed from our senses. But, contrary to Kant, who held that these basic categories were necessary and unrevisable, we find that these intellectual building blocks do change over time with advances in the sciences and force us to radically revise how we make sense of ourselves and our environment. This provides fertile ground for the creative arts. The freedom they enjoy to reflect the world in novel and sometimes strange ways which can inform and influence the scientists who are often in need of new and exciting ways to try to organize the seemingly strange results they receive from the universe. So, sometimes art and science influence each other, but often not. There was a tension between the Enlightenment-influenced rationalists and thinkers who were romantically inclined. Those who latched onto reason would put forward the progress that science and technology made as evidence to support their foundational views. The use of reason gave us justified beliefs that could come from nowhere else. First and foremost amongst these were the propositions of mathematics. They and they alone provided humanity with truths that were absolutely certain, undeniably true. René Descartes in the 17th century, one of the founders of this rationalist movement and a major contributor to physics, mathematics, and philosophy, thought that the methods of the mathematician were so impressive that they ought to form the backbone of all further investigations. In all other areas of conversation, smart people disagreed about everything, but in mathematics, you have universal assent. You had facts that could not be challenged by anyone who understood them and complex results that were derived from them with absolute rigor. Mathematics was a thing of beauty, an absolute bedrock on which we could construct a completely firm structure of understanding. When Isaac Newton mathematized physics a generation later with his invention of calculus, it seemed like the rational worldview based on mathematics was well on its way to giving us an unassailable sense of reality itself. Mathematical propositions were self-evident, true beyond question. Those who doubted them showed themselves either to be lacking in understanding, mentally deficient, or just trying to be irascible. And so it's difficult to overstate how worrisome it was when, in the 19th century, the very foundations of all of mathematics came into serious doubt. Traditionally, we've thought the mathematical realm as having two parts. Geometry deals with shapes in space, and arithmetic deals with matters of number. Both had been rigorously grounded, we thought, and while there were interesting works showing some interconnections, we thought we had two different but equally justified areas of knowledge. And then, things fell apart in both. Now, since the 3rd century BC, geometry was synonymous with the name Euclid. There had been centuries of work on geometry before Euclid, but what he did was take these results and order them. He created a structure based on a few simple and obvious propositions and used a strict means of reasoning to derive hundreds of complex and intricate theorems. These theorems, because of the rigor of his logic, must share in the certainty we attribute to the first most basic truths. These basic truths come in 3 groups. First are the definitions that simply describe what we mean by our basic geometric terms. A circle, for example, is the set of points in a plane some distance from a center point. In other words, pick a point, move a number, and now move that number of units away, and in any direction, you get the set of points that makes a circle. I use this definition myself. When I was in high school, I used to make extra money by lining the field for the lacrosse team. Goals on a lacrosse field sit inside of a circle with a 9-foot radius. So I put a stake in the ground in the middle of the goal line, get a rope that was 9 feet long, and lay down a chalk line by keeping the rope taut as I moved around the stake. Voila, a circle. Now, definitions are true. They're true because they simply tell us what we mean by words. We're free to define any word in any way we want. As such, Euclid's definitions have to be true. That is, they're true by definition. But there are 2 other categories of basic truths that he used. One are Euclid's axioms. The axioms were basic, obvious truths that were not explicitly geometric. For example, equals added to equals yields equals. If John and Susie have the same number of apples, and I give them each some additional number of apples, right, giving them the same, then each still has the same number of apples as the other. How can you argue with that? The postulates are similar, except they are about purely geometric matters. Give us any 2 points, and we can draw a line between them. Give us any line segment, and we can continue that line as far as anyone wants in either direction. Give us a point, and we can draw a circle around it any size we want. All right angles are equal to each other. No one could possibly doubt these. So what I've given you are the first 4 of the postulates. Now, if the first 4 are the fingers on the Euclidean hand, the 5th is the sore thumb. It sticks out. It seems different. Euclid put it like this, that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, these straight lines, if produced indefinitely, will meet on that side on which the angles are less than 2 right angles. In other words, if 2 lines are approaching each other, they'll eventually intersect. We usually think of it in terms of an equivalent formulation. Take a line and a point not on that line. How many lines can we draw through the point that will be parallel with the line? 1 and only 1. This postulate seemed less like the others and more like Euclid's theorems, that is, the statements he proved from the other postulates. So, maybe it's a theorem. That is, maybe it would be possible to derive it from the other 4. This would be a big deal, because one thing mathematicians prize is elegance. A system is elegant if it makes the fewest possible assumptions. To show how we could derive the 5th postulate from the other 4, making it unnecessary as an assumption, it would shrink the set of presuppositions, and this would improve the system, Euclid's system, the greatest and seemingly most elegant and powerful system of all time. Improving Euclid would be like improving Shakespeare. It would assure one's place in the annals of mathematical history, and thus much time was spent by brilliant people for centuries seeking the elusive proofs of the 5th postulate, the so-called parallel postulate. But it was never found. Turns out there's a reason it was never found. It doesn't exist. You can't improve on Euclid as mathematicians had hoped. The 5th postulate is entirely independent from the other 4. But we only found this out the hard way. After mathematicians had failed in all their attempts to create a direct proof from the first 4 to the parallel postulate, the idea occurred to several different mathematicians to try what's called an indirect proof. Now, we can show that something is true by demonstrating that it can't be false. If you know that I have a sibling and you want to prove that I have a brother, it suffices to prove that I can't have a sister. If I have a sibling and it's false that I have a sister, then it must be true that I have a brother. What mathematicians wanted to prove is that Euclid's fifth postulate can be derived from the other four. That means that the truth of the other four postulates guarantees the truth of the fifth. So, we start by assuming the opposite, that the other four postulates are true and that the fifth is false. Then we derive a contradiction. That is, any sentence of the form A and not A. Since either A or not A has to be true, but both can't be, the contradiction A and not A has to be false. The existence of this contradiction shows that if the postulates 1, 2, 3, and 4 are held to be true, then the denial of the fifth can't be true. But if the denial of the fifth is false, then the fifth has to be true. This would show that Euclid could be simplified. But when mathematicians assumed 1, 2, 3, and 4 in the negation of 5, they worked and worked and worked, but never found a contradiction. They found weird results. Things like, you can't have triangles with the same angles but of different size. The internal angles of a triangle add to less than 180 degrees. Bizarre stuff. Statements that seemed like they were false, but never a contradiction that had to be false. In the first half of the 19th century, the Russian mathematician Nikolai Lobachevsky, among others, realized that they had found something incredibly deep and troubling. They had in their hands a new geometry, a different geometry, a non-Euclidean geometry. This strange world was a new mathematical realm, if you'll pardon the pun, a parallel mathematical universe. But if we have two geometries, which one's true? When we had only Euclid's, we assumed that it gave us the absolute truth about the nature of shape and space. But if there's a possible alternative, we can't hold its truths to be absolute. We need a new sort of evidence to justify our belief in what seemed indubitable. But what kind of evidence could this be? We can't simply say that the alternatives are too weird. Being weird doesn't make it false. To make matters worse, more systems were created by denying other postulates and combinations of postulates. Possible geometric systems were popping up right and left. Which one was true? Which one is the real geometry? How do we know? What had been the most secure place on the entire intellectual landscape for over 1,000 years was now suddenly without a foundation. Mathematicians were not happy. But at least we had the other side of the mathematical house, right? Arithmetic was still safe and secure. 1 plus 1 is 2. There can't be any reason to doubt that, right? We had thought that numbers were well behaved, that they obeyed certain undeniable first truths. Think back to Euclid's axioms. We considered the first one, equals added to equals yields equals. But now let's think of the fifth axiom. The whole is greater than the parts. If I have an amount of money, and in my will I leave some of it to a relative and the rest to a charity, neither heir gets as much as I previously had in sum. By getting part, both get less than I had in aggregate. This seems trivial and obvious. Of course, always true, right? In the second half of the 19th century, the German mathematician Georg Cantor showed this is not the case. Now, suppose we have a mutual friend named George, and next week is George's birthday. We want to get him something we know he'll love as a gift. What to get him? You remind me he's an avid collector of numbers. Now, we talk to his wife, and she tells us that his collection now includes all the positive integers. He has 1, 2, 3, 816, 9,674,217. He's got them all. Right? If he has all the numbers you could count from 1 forward, hey, we'll get him the one before 1. We'll give him 0. So, the big day comes, and after blowing out his candle, he opens his gift, sees his new 0, a number he didn't have before. Overjoyed, he looks at us with tears in his eyes and says, "Thanks for nothing." So, George's number collection now has 1 more than it had before his birthday. So, it's bigger, right? The pre-birthday collection is only a part of the whole, so the whole is larger than the part, right? Wrong. He still has exactly the same number of numbers. Huh? Okay. Suppose we go to a movie theater, and we want to see if the show is sold out, undersold, or oversold. Since all people have but one backside, and we use that backside to sit in but one seat, we could count the number of seats in the theater, count the number of backsides, and see which number is bigger, or if they're equal. But Cantor realized we could do it in a way without counting at all. Ask everyone to sit down. That is, match every available seat to an available backside 1-to-1. Then, see if there's a remaining seat, a remaining backside, or neither. This is a way to compare the size of sets without counting. Two sets are of equal size if there exists a way to map the members of one set onto the members of the other so that each element in the first set corresponds to one and only one member of the second with none left over. So let's do this with George's numbers. If we take each of the numbers in his post-birthday collection, can we map it to one and onto only one from his pre-birthday collection? Take each number in the collection after his birthday and map it onto that number plus 1 in his old collection. That is, 0 goes on to 1, 1 goes on to 2, 2 goes on to 3, and so on. In this way, in the end, there will be no number in one that doesn't have a correlated number in the other. This maps one set perfectly onto the other set. The two collections are the same size. George's extra number has made his collection no larger, even though it now includes a new element above and beyond what it had. For an infinite number, the number of counting numbers, that infinite number plus 1 yields the same number. All right, that's weird. But we might think, okay, it's all because it's an infinite number of numbers, right? You can't make infinity bigger. It's infinity, right? It's already infinite. How could you make it bigger? But all we just showed is that infinite amounts are as big as one can get. You can't have a smaller or bigger infinity. Nope. This is where Cantor's work gets fun. Consider the numbers between 0 and 1. Some of these are what we call rational numbers. That is, they can be written as ratios. 1/2 is 1/2. 3/4 is 3/4. These can be written equivalently as decimals. 1/2 is 0.5. 3/4 is 0.75. Interestingly, all of these numbers will have one of two properties. Either they will terminate, that is, like 1/2, they'll end, 0.5, done. Or they will repeat. 1/3 is 0.33333333, and as far as you go, there will always be more 3s. 1/7, when written as a decimal, is 0.142857. 142857. 142857. And as far as you go, there will always be another 142857. This is the case with all ratios. They terminate or they repeat. But then there are the numbers that do not repeat or terminate when we write them out as decimals. These are what we call the irrational numbers. Not because they're crazy, but because they can't be written as a ratio of two counting numbers. The most famous, of course, is pi. 3.14159, and off we go forever. Always another digit, never repeating endlessly like the 3s of 1/3 or the 142,857s of 1/7. If you take the rational numbers and combine them with the irrational numbers, you get what we call the real numbers. Now, suppose George has an older brother, Frank, who's been collecting numbers even longer. He's amassed all the rational numbers between 0 and 1. 1/2, 1/4, 9/16, all of them. He then orders from an online retailer the set of irrational numbers between 0 and 1. When it arrives, he now has both the infinite set of rational numbers between 0 and 1 and the infinite set of irrational numbers between 0 and 1. That is, he has all of the real numbers between 0 and 1. Now, we might think that, like George on his birthday, his new set with more numbers is exactly the same size as it was before. Infinity is infinity. You can't get larger than infinity. But you would be wrong. Cantor proved with absolute certainty that Frank's new set is bigger. It is a bigger infinity. There are sizes of infinity. If we map his old set onto his new set, Cantor showed that there's a simple way to show that the new set has at least one number that can't be in the old set, which means the new set is bigger. So, some infinite subsets are the same size as the sets that include them, and other infinite sets are bigger than others. In fact, there would be an infinite set of infinite numbers, and these obey different rules than the finite numbers. So, which number rules are true? The easy answer would be that there's one set of rules for finite numbers and another set for infinite ones. That was the line mathematicians pursued until 1931, when the Austrian mathematician Kurt Gödel proved that we could not set out a complete set of rules for arithmetic. Gödel showed that we could use any set of possible rules to create sentences similar to the sentence, "This sentence is false." Right? If it's true, then it's false, but if it's false, then it's true. Any attempt to create rules would either allow sentences like, "This sentence is unprovable," to be proven. And so we would have sentences that can be proved but are false. We would have just proven the sentence that says it can't be proven. Alternatively, we could strengthen our rules to exclude these sentences. But then, because we can no longer prove the sentence, "This sentence is unprovable," would be true. And so we would have true sentences that we can't prove in our system, making our system incomplete. Any set of rules would be either unsound, that is, include false sentences, or incomplete, not allow all true sentences to be proved. The days of mathematics, as the epitome of human rational understanding, seemed to close at the end of the 19th, beginning of the 20th century. It was the canary in the intellectual coal mine. Interestingly, we see this collapse of certainty and the wide-scale wreckage it would cause to the foundations of our reason reflected in a pair of notable and related works of fiction coming out of Britain in the late 1800s. Lewis Carroll's Alice's Adventures in Wonderland and Edwin Abbott Abbott's Flatland, a romance of many dimensions. Alice in Wonderland, as the tale has come to be known, and its sequel Through the Looking Glass, were written by Lewis Carroll, the pen name of Charles Ludwig Dodgson, a mathematical logician at Oxford. Because of the ascent of non-Euclidean geometry and the attempts to find a firm foundation for arithmetic and set theory, the world of mathematics had turned its attention largely to logic in hopes that an analysis of the nature of mathematical reasoning would yield a justification that was needed to keep mathematics as the hardcore basis of all that was absolutely certain. But mathematicians are a strange lot. While they understood the gravity of the circumstances, they also found themselves drawn to the paradoxes that could be created when these foundations were examined creatively. The heart of traditional logic is the law of the excluded middle, the claim that either a sentence or its negation, but not both, must be true. Either I have a brother or I don't. I can't both have a brother and not have a brother. And if I know that one claim is true, I know the other's false. And if I know one is false, then I know the other's true. A paradox is a sentence or set of sentences which contradicts itself. That is, it must be true, but then its truth implies its falsity. Since the law of the excluded middle holds that a sentence can't be both true and false, we have an affront to the basis of logic itself. Logicians like Dodgson were examining purported paradoxes generated by the logical system itself, which, if authentic, would undermine the underpinnings of our most rigorous form of thought. This is what he was doing in his professional published work, but it's also what he was playing with in his famous work for children. Think of the opening scene in which Alice spies the white rabbit taking a pocket watch out of its waistcoat and declaring that he'll be late, and then dashing down a hole into which Alice follows. Carroll famously wrote that either the well was very deep or she fell very slowly, for she had plenty of time as she went down to look about her and wonder what was going to happen next. So Alice fell for a long time. This means that either she fell at a normal rate down a well that was very deep, the normal inference, or that the well was not deep, but she fell at a slower rate. Now remember that Dodgson is British, and the most celebrated intellectual figure in Britain was Isaac Newton. Newton's laws of motion explain the finding of Galileo that all objects close to the surface of the Earth fall at exactly the same rate. If we're taking seriously the possibility that Alice is falling slowly, then we're taking seriously the possibility that the immutable laws we take as part and parcel of the working of the universe no longer apply. We've entered a realm where the Enlightenment presupposition of a well-behaved universe whose rules are accessible to our rational faculties can be reasonably denied. Reason implies nonsense. Reason is not ultimately self-justifying, but ultimately self-defeating. Wonderland represents the death of the rationalist project. Think of Alice's encounter with Humpty Dumpty in Through the Looking Glass. Now, the two are discussing birthdays and birthday presents when Humpty Dumpty explains, "There's glory for you," to which Alice replies, "I don't know what you mean by glory." To quote the passage, Humpty Dumpty smiled contemptuously. "Of course you don't. Till I tell you. I meant, there's a nice knockdown argument for you." "But glory doesn't mean a nice knockdown argument," Alice objected. "When I use a word," Humpty Dumpty said in a rather scornful tone, "it means just what I choose it to mean, neither more nor less." "The question is," said Alice, "whether you can make words mean so many different things." "The question is," said Humpty Dumpty, "which is to be master. That's all." In Greek, a language that Dodgson spoke, the word for word is logos, which also means in some contexts logic. When he has Humpty Dumpty redefine the word glory, it's not a random sense, but rather a nice knockdown argument. That is, the goal of logic. When Alice protests, Humpty Dumpty replies that the real question is who is to be master, humans or words? That is, which ought to be the measure of reality, our experience, our freedom, our lives, or logic? Should we be subservient to our reasoning as the Enlightenment influenced rationalists would have? Or should we take command over logic, over words, over logos? If we follow logic, do we disappear down a rabbit hole? Something that seemed possible given the paradoxes that mathematical logic was generating. We find a similar challenge in Abbott's Flatland, which takes place on a two-dimensional plane. It's a flat world populated by shapes, the narrator being a lowly square. See, in Flatland, the more sides you have, the higher your social position. The square is visited by a sphere, a three-dimensional figure that appears to the square at first as a point, then a circle of increasing diameter, then a circle of decreasing diameter, and then a point. Finally, a disembodied voice. The sphere tries to convince the square of the existence of a third dimension without any success until he flings the square out of his planar world into the space above it. Upon returning to Flatland, the square becomes evangelical about convincing his fellow Flatlanders about the existence of this third dimension that is upward, not northward, a dimension they haven't seen. He's arrested and charged with heresy by the high priest, and at his trial, he is asked to provide any evidence for the existence of this third dimension of which he so passionately speaks. His argument is mathematical. If we can take a point and move it, we get a line. If we take a line and move it parallel to itself, we get a plane. If we take that plane and move it parallel to itself, we get space. The priest asks for physical, not mathematical reasoning. The square can provide none, and so the priest gives his argument that there is no reason to think that this mathematical talk is anything but trickery with no relation to anything real. The argument's compelling. All the while, the reader knows it's wrong, but it's reflective of the strange results coming out of mathematics at the time. They threaten to undermine our comfortable, certain basis for rationality. But should they be accepted? Has reason led to nonsense? Or is there a foundation for rational thought to be found in rational thought? For over 1,000 years, we accepted Euclid's axioms and postulates as true because they were self-evident, seemingly self-justifying. But at the dawn of the 20th century, mathematics, our most secure and definitive science, was in turmoil. We were forced to re-examine the basis of what we thought reality would be like. Lewis Carroll's Wonderland was about to be discovered here in our world when the science of the 20th century forced us to reconsider reality itself.